Hello, we're team, and the main goal of our final project was to perform hate speech detection. Before we continue any further, it's important to first define hate speech. According to the Cambridge Dictionary, hate speech is defined as public speech that expresses hate or encourages violence towards a person or group based on something such as race, religion, sex, or sexual orientation. During the COVID-19 pandemic and widespread social movements, hate speech has been increasingly prevalent in the United States. Such speech has been directed towards perceived sources of the virus, such as Asian and Chinese Americans, and has also risen in response to the Black Lives Matter movement. Many individuals, organizations, and corporations are pursuing better methods of detecting and combating hate speech as a result.
Online platforms like Twitter and Facebook have facilitated spaces for hate speech as people are bolder in voicing their opinions through their screens. And last year alone, Twitter saw a 900% increase in hate speech towards China. Furthermore, hate crimes in the US have reached their highest level since 2008, with an estimated 250,000 hate crimes a year. There are also a lot of challenges when it comes to hate speech detection. Some complicating factors include sarcasm, slang, sociopolitical context, and much more. As hate speech is constitutionally protected in the US under the First Amendment, there is no legal definition of hate speech or laws regulating it. This makes detection difficult as one must first define it and then use data labeled according to that definition.
This is also reflected in our dataset. We use the Twitter hate speech dataset, which is a very common dataset that has been used across various papers pertaining to hate speech. The dataset contains 25,000 tweets from Twitter, and it labels them as hate speech, offensive, or neither, through majority voting by annotators at Crowdflower, also known as Figure 8, which is a machine learning and AI company. Looking through the dataset, we immediately noticed a skewed distribution with the offensive speech category making up 77% of the dataset. Furthermore, we saw an overlap of offensive speech with hate speech. Because this dataset was labeled by majority voting, there is no true label. It depended on human perception, which is very difficult to estimate as we discussed earlier. A lot of offensive language seemed to consist mostly of foul language, thus it did not seem very representative of a more general population, as there are a lot of ways to be offensive without just swearing. Although we noticed these potential problems with the dataset, we also observed that these problems were not unique to this particular dataset. They were shared to some degree by all of the datasets that we explored. One important thing to note is that there is no standard dataset that is used in hate speech detection, so there was no obvious choice for us to make. However, in the papers we referenced, the Davidson dataset was widely used, so we decided to use it as well.
To better represent our models and fine-tune our algorithms, we decided to use feature engineering to represent our data points. Our first representation was bag of words, which finds the words that most commonly appear together, and labels test data based on associations between the label and common words used in training for that data. Essentially, it just highlights the more frequent words, which would make sense with our data set because it would associate slurs with hate speech. But this ended up just blurring the line between hate speech and offensive speech because tweets in both of these categories were riddled with slurs. Next, we considered TF-IDF. This one's a little smarter than bag of words because it accounts for document frequency and not just the frequency of words. So we basically just highlighted the more frequent words in a document, but infrequent across all documents. But this wasn't particularly helpful for our data set. It heavily focused on offensive language and hate speech, so a lot of the foul language is actually expected to show up across tweets. But our hate speech data points were generalized slurs not targeting a specific group, so the slurs themselves were not necessarily very frequent within a tweet. We believe that TF-IDF would have been better if our data set was focused on a specific category of hate speech like race or sex, since it would have increased the frequency of slurs within the document, but not necessarily across all the other neither or offensive label documents, which would have highlighted the slurs as more important features. And finally, we decided to choose Doc2Vec, which incorporates Word2Vec, but instead of representing a single word, we wanted to represent the whole tweet. So we utilized Doc2Vec embeddings that learn semantic contextual relationships between the words and their vectors. The number one thing lacking in our previous two options is that neither of them incorporate any grammar or context in their embeddings. So for this presentation, we decided a good way to compare the models we used is to put them in a tier list. The tier list order is modeled after OSU's grading scheme this semester, where A is the best possible tier for the models, which performed very well with our data set, and no pass for models which performed very poorly. Our first model that we built was a naive Bayes model, which will assume independence between features that we engineered and attempts to draw correlations between these features, which represents words, and the class of the tweets the words came from. The model is a rather simplistic approach and was very easy to implement, but the results were quite underwhelming. On paper, a 78 accuracy score doesn't seem too bad, but upon further inspection of the classified data, naive Bayes was never able to successfully classify hate speech, and all the accuracy is a result of classifying offensive and neither labels correctly. The small improvements from TF-IDF over bag of words likely come from the fact that multiple instances of a word within the tweet are weighted higher than bag of words. Having seen the results from naive Bayes, we've decided to put naive Bayes as a no pass. This is because our goal was to identify hate speech, which it literally never does. In fact, we would be better off rolling dice than using naive Bayes because it would at least sometimes identify hate speech.
KNN is another popular text classification algorithm based on a similarity metric. After tweaking the algorithm using different distance metrics and number of neighbors, we landed on using 5 neighbors and the Minkowski distance metric. The algorithm was tested with cosine similarity as a distance metric for doc to vec, but there wasn't a noticeable improvement or deterioration in performance. Since the cosine similarity metric doesn't satisfy the triangle inequality, it wasn't a suitable distance metric for KNN. We see that TF-IDF performs the best in KNN. However, even with a decent accuracy of 84%, the F1 score is not as great. We notice that the data imbalance has a greater impact in KNN because the algorithm classifies based on the labels of its neighbors. As we saw earlier, 77% of the dataset is offensive data points. Thus, a majority of the neighbors will be offensive data points. Furthermore, a lot of offensive data points contain foul language, and this language is also seen commonly in the hate speech data points. So it's really easy to classify a hate speech data point or neither data point as offensive due to these factors. Because of these reasons, we felt that KNN wasn't a very suitable classification algorithm for this particular problem in this particular dataset, so we classified it in Tier D in the tier list.
We then tried logistic regression, so this is another relatively simple method that essentially models a sigmoid function that reflects probability. But even though it's so simple, it's actually very fitting for our use case in that we don't have a perfect separation of where we're able to classify something definitively as hate speech. With that being said, here's a quick overview of our results. As you can see from the slide, when using a cumulative test set, logistic regression performed very well with all of our attempted feature engineering methods with accuracy scores in the mid to high 80s. When looking at a test set of just hate speech, the model using TF-IDF has a much higher accuracy in comparison to bag of words. At a glance, bag of words look to have a very high accuracy, yet when classifying just hate speech tweets, its accuracy dropped to 46%. You might recall that our dataset had a large disparity between offensive tweets and the other classes. With the bag of words feature engineering, the threshold to classify a tweet as hate speech or neither may be very high, and the features may not be very refined. This may result in the model classifying more tweets as offensive than it should. This is the first model thus far where TF-IDF's inherent nature to penalize frequent words with low document frequency has been useful. Overall, we see logistic regression with TF-IDF feature engineering as a very viable option.
The next model we use was BERT, which can be used for both encoding and classifying, or use another classifier after encoding with itself. We decided to use BERT for both, as to have simpler results and more fine-tuning of BERT itself. BERT's encoding model stands out from others by using context to embed words. This allows it to take into account other words in the sequence to determine the embedding for a word. This encoding can be used pre-trained and also trained manually. We used a pre-trained embedding model as to reduce energy consumption while still having a very well-trained model. After embedding, we then trained BERT's classifier on our training word vectors and classified test and validation sequences. Our early results were confusing. We got a high accuracy in the 70% range overall, but we failed to classify any of the hate speech category. To remedy that, we reconfigured our formatting and implementation, and simplified using binary classification. Using the categories hate and not hate instead of hate, offensive, and neither, we got promising accuracy of 80% overall, and 77% for the hate speech category specifically. We witnessed a large boost around 70% accuracy overall to these numbers when going from 10 to 75 epochs, with gains being marginal after that. We also fiddled with different learning rates and architectures, but we didn't have any notable improvements from that. We're a bit confused as to why this wasn't our highest performing model, given it's the most advanced. Other papers and guides we referenced achieved over 90% test accuracy on similar tasks. We can maybe attribute this to having a different setup and a different suboptimal network or setting configuration. Additionally, our dataset might just be more difficult to classify overall. BERT performed very well, but as it didn't beat logistic regression, it's B tier instead of A tier. We believe that with more fine-tuning, BERT could have easily reached A tier.
Hate speech detection is a very complex problem to solve. However, if we were to approach this problem from scratch, there are several things that we would do differently. The first is concerning our dataset. We decided to use the Davidson dataset since it was commonly used across many papers. However, we believe that adding the option to label data as offensive really complicates an already complicated problem. In several of the algorithms, it made it almost impossible to determine the hate speech due to the overlap between the classes and also due to the skewed distribution. We would look to using a binary dataset that distinguishes between hate and no hate, or perhaps a more equally distributed dataset where there are clearer distinctions between the classes. Next, as discussed earlier, our dataset doesn't seem to fully take advantage of TF-IDF since hate slurs or foul language is not necessarily uncommon across or within documents, as our dataset heavily focuses on hate speech and offensive language. We believe that with the dataset more focused on a specific category of hate speech and more distinct and equal classes, we would be able to better leverage TF-IDF. Finally, in terms of our approach to the problem, we seek to implement a variety of algorithms and embeddings. Thus, we often found ourselves spending a lot of time on implementing and understanding the details of certain algorithms and how we expected it to work with our dataset, which ultimately prevented us from trying to fine-tune every model to the degree that we would have liked. We believe a better approach would have been to pick one or two algorithms with one or two embeddings and focus mainly on those. Shown here are the sources and papers that we've referenced in the process of completing this project.